Hello and welcome to Lecture 5 from Interlude B from our text, A Surface Veneer, Sediments and Soils. This image that we're looking at is the Siletz River Estuary, where sediments have collected in Siletz Bay, Oregon. High rainfall erode the Oregon Coast Range in the background. The sediments are transported by the Siletz River to the Siletz Bay, where they are deposited at or near sea level. In the Oregon coastal environment, soils quickly form on the sediments and grass roots in the soils. Sediments and soil form a veneer that cover the bedrock, in this case the Astoria formation, in the embayment. In this lecture, we will cover how rocks undergo change at or near the Earth's surface due to weathering, how weathering produces sediments, the difference between sediment and soil, and finally factors that affect the character and thickness of soil. It is my hope that by the end of the chapter you will have a better understanding of the erosional processes and the soils that are produced from these sediments. In Figure A, we are looking at a cross-section of the Nile River Valley, originally obtained in 1950. Evidently, at some point or some time in the geologic past, the Nile River had carved a canyon 1,500 meters deep, and subsequently this canyon filled with sediment. The surface of a river where it empties into the sea cannot be lower than sea level. Geologists of the 1950s were perplexed and couldn't understand how this could happen. It remained a mystery until 1970 when geologists began to study the Mediterranean sea floor by drilling into it. Figure B. They expected to find layers of sediments containing fossil plankton and mud. They did find the layers of plankton and mud, and also, to their surprise, the drill penetrated a 2-kilometer thick layer of halite and gypsum. These minerals form only when sea level dries up. Figure A. The layers of salt indicate that the Mediterranean had dried up repeatedly over a long period of time. Also, when the Mediterranean Sea dried up, the Nile River would have flowed into a basin whose floor was 1,500 meters lower than today. So over time, the river cut a canyon down to the low elevation of the dry seafloor. Later, when the Strait of Gibraltar opened up and allowed the Atlantic to refill the Mediterranean Sea, the river could no longer cut down and the flooded canyon filled with sediment brought from upstream. Geologists refer to the kinds of river deposits just described as sediments. Sediments, broadly defined, consist of loose fragments of rocks or minerals broken off of bedrock, or mineral crystals that precipitate directly out of water, or shells or shell fragments. The sediments may be sand, mud, gravel, salt, such as halite and gypsum, and shell fragments. We will discuss sediments and sedimentary rock in detail in the next lecture. Photograph A is an example of gravel, sand, and mud that have washed or tumbled to a valley floor in California. Photograph B shows shells that have accumulated on a beach in Florida and later break into smaller pieces by wave action. And photograph C shows salt precipitates on fence posts protruding from the Dead Sea, which is an extremely salty lake. Sediments are produced by weathering, the physical and chemical breakdown of rock at the Earth's surface. They form a surface veneer or cover over bedrock that range in thickness from millimeters to kilometers in sedimentary basins. Water and organisms may modify sediments over time and transform them into soil. The average soil thickness is about 1 meter. The soil produces and sustains minerals that plants and animals need for life. That includes humans. The Earth's radius is about 6,370,000 meters, of which only the outer 1 meter provides the sustenance needed for life. That's a very important layer, and sooner or later almost all of our toxic byproducts are filtered through that layer. Geologists use the term regolith for any loose materials such as sediment or soil that cover bedrock at the Earth's surface. At the Earth's surface, any outcrop or fresh rock or newly exposed rock does not last forever due to weathering. Weathering refers to the process that breaks up and corrodes solid rock into loose debris or detritus. In the photographs, we see the contrast between fresh and weathered granite in an Arizona outcrop. Weathered granite can break apart. The grains fall off and collect as regolith. The insets show how weathering physically changed the rock. Physical weathering, also referred to as mechanical weathering, breaks intact rock into unconnected clasts. Clasts are individual grains or chunks of rocks. That's CLASTS. Clasts are individual grains or chunks of rock. Each size range of clast has a name as shown in Table B.1. You need to be familiar with this table. Boulders have grain diameters greater than 256 millimeters or 25.6 centimeters. Cobbles range in grain diameter between 64 millimeters or 6.4 centimeters and 256 millimeters or 25.6 centimeters. Pebbles fall between 2 millimeters and 64 millimeters or 6.4 centimeters. Sand ranges between 1/16 of a millimeter or 0.0625 millimeter and 2 millimeter. Silt grains fall between 1/256 millimeter or 0.039 millimeter and 1/16 or 0.0625 millimeter, and mud is less than 1/256 millimeter or less than 0.0039 millimeters. Physical erosion processes can include joining, frost wedging, root wedging, and thermal expansion. Joints are natural cracks formed in rocks due to either expansion of a rock undergoing exhumation, which causes stretching from removal of overburden by uplift and erosion, and/or by cooling and contraction. Joints come in a variety of forms. Some have smooth planar surfaces, whereas others have irregular, jagged surfaces, and still others trace out broad curves. In example B on the slide, vertical joints break bedrock into blocks and sheets that fall to the base of cliffs, or in example A, exfoliation joints on this granite mountain slope in the Sierra Nevadas break the rock into onion-like sheets that are parallel to the rock's surface. Frost wedging. When water trapped in a joint freezes, the ice expands in size, exerting pressure and forcing the joint open, and may cause the joint to grow. Frost wedging helps break rock free from intact bedrock. Tree roots that grow into joints can push joints open in a process known as root wedging. In this example, the tree roots are growing in a joint in some sandstone in an arid environment. The roots exert pressure and weaken the rock. Eventually, the rock breaks free from the outcrop and tumbles to the valley floor. Salt wedging. In both arid and coastal environments, dissolved salts in water precipitates and forms crystals in open pore spaces in the rocks. As the crystal grows, they expand and weaken the rock, allowing wind and rain to further weaken the rock. Salt wedging on limestone tombstones in Whitby, England, and at Salt Point State Park, Sonoma County, California, produces a honeycomb weathering texture. Intense heat can cause rock to expand, and on cooling, the rock contracts and breaks off in sheet-like scales. This may occur in two ways. One, due to forest fire, or two, by repeated heating and cooling of rock during day and night cycles, which causes the same expansion and contraction and finally breakage over time. Animal life also contribute to mechanical weathering. Burrowing animals weaken rock and cause breakage. In addition, blasting and excavation by humans, we shatter and displace rock that might have remained intact for millions of years. Chemical weathering refers to the chemical reactions that alter or destroy minerals when rock comes in contact with water solutions or air. Common reactions active during weathering include the following, or rather during chemical weathering include the following: dissolution, hydrolysis, oxidation, and hydration. During dissolution, minerals separate into ions that become surrounded by water molecules and are glommed onto the water molecule. The ions in the water then join groundwater or rivers and streams, where it may later either precipitate out as sedimentary rock or evaporate, forming evaporites. Rainwater is slightly acidic by absorbing carbon dioxide from the atmosphere. When it falls, it mixes with organic matter, forming an even stronger carbonic acid. This acid is strong enough to break carbonate rocks such as limestone, dolomite, or marble into calcium ions released to the water, and bicarbonate, which either is released back to the atmosphere or further strengthens the acidity of the water. See image on the right. In the photograph on the left, the regolith has been stripped of soil, exposing the eroded fractures of the limestone bedrock. Chemists refer to a reaction during which an element loses electrons as an oxidation reaction. Such a loss commonly takes place when elements combine with oxygen. Oxidation reactions in rocks transform iron-bearing minerals such as biotite mica or pyrite into various iron oxides and iron hydroxide minerals. It becomes rust-colored. During hydrolysis, water reacts chemically with minerals and breaks them down to form other minerals. An example is potassium feldspar, or found in granite. It reacts with acidic water to form kaolinite, a type of clay, along with a variety of dissolved ions. It occurs in other silicate minerals as well. Hydration is the absorption of water into the crystal structure of minerals, causing certain minerals such as clay to expand and weaken the rock. During hydrolysis, water reacts chemically with minerals and breaks them down to form other minerals. An example is K-feldspar, or potassium feldspar, found in granite. It reacts with acidic water to form kaolinite, a type of clay, along with a variety of dissolved ions. It occurs in other silicate minerals as well. During the hydration process, water is absorbed into the crystal structure of the mineral, causing certain minerals such as clay to expand and weaken the rock. So dissolution dissolves the rock, breaking the minerals into ions, which are later precipitated or evaporated into new minerals. Oxidation occurs when a mineral loses an electron and combines with a water molecule to form a new mineral. In hydrolysis, the water chemically alters the original mineral into a new mineral, and during hydration, water is absorbed into mineral crystals, into the mineral's crystal structure, causing expansion of the mineral. Not all minerals undergo chemical weathering at the same rate. Some weather in a matter of months or years, whereas others remain unweathered for millions of years. Minerals that form in Bowen's reaction series are among the least stable on the Earth's surface. Minerals that form from the products of weathering reactions are among the most stable minerals at the Earth's surface. Mafic minerals weather by oxidation, felsic minerals by hydrolysis, carbonates and salts by dissolution. Oxide minerals don't weather at all. Figure A illustrates that as rock breaks apart by physical weathering, the surface area increases relative to volume. Figure B illustrates that as the rock breaks into smaller and smaller pieces, the surface area increases. So chemical weathering happens faster and faster. Eventually, the rock disaggregates to form sediment. Here, the weathering of granite produces quartz sand and silt and clay particles. Quartz and clay are two very stable minerals. That's why river valleys, beaches, deltas, and offshore deposits are mostly quartz and clays. Weathering happens faster at edges and even faster at the corner of broken blocks because weathering attracts a flat surface from only one direction, an edge from two directions, and a corner from three directions. Over time, edges of the blocks become blunt and corners become rounded. When different rocks in an outcrop undergo weathering at different rates, we say that the outcrop has undergone differential weathering. Weak layers weather away beneath a more resistant layer, so that the resistant layer becomes an overhanging ledge. The outcrop may take on a stair step or a sawtooth shape. The rate at which land surface weathers depends on the rock type. So valleys tend to develop over weak rocks, while strong rocks hold up hills. The erosion of the bedrock modified by physical and chemical interaction with organic material and water that is capable of supporting life is the book definition of soil. Soil is not dirt. Dirt is what accumulates under your fingernails, between your toes, or the grime in your clothes. Soil is that meter-thick layer that grows plants and supports insects and other faunal life. The picture shows a regolith, the soil layer above the chalk limestone bedrock. There are three processes that take place at or just below the surface of the earth that contribute to soil formation. 1. Production of mineral debris by chemical and physical weathering produces loose debris, new minerals like clay, and ions in solution from sediment or bedrock occurs in the zone of accumulation as shown in figure A on the left. 2. Interaction with water when rain falls. Some of the water percolates down through the debris and transport clay particles and ions downward through the zone of accumulation. The zone of downward transport is called the zone of leaching. As the water passes down through the zone of leaching, new mineral crystals precipitate out of the ion-rich water and collect with the fine clay particles in the zone of accumulation. And 3, interaction with organisms leave behind organic waste, produce acids that weather soil, and also physically churn, break up the soil, and die and rot. The organic material within the soil makes up humus found in the O and A layer of the next slide. Because different soil forming processes operate at different depths, soils typically develop distinct zones known as soil horizons, arranged in a vertical sequence called a soil profile. Looking at an idealized soil profile of temperate forest soil from top to bottom, we start with the O horizon. The O horizon, or organic horizon, consists almost entirely of organic matter and barely any mineral matter. It is the layer of duff, dead grass, leaves, and twigs that accumulate on the surface of forest soils. Below the O horizon is the A horizon, in which humus has further decayed, mixed with mineral grains of clay, silt, and sand. This is the layer that is commonly called topsoil, the fertile portion of soil that farmers till for planting crops. In some places, the A horizon grades downward into the E horizon, a soil horizon that has undergone substantial leaching but is not mixed with organic material. This horizon is often called the transition zone. So the O, A, and E horizon lie within the zone of leaching. Below this, ions and clays accumulate in the B horizon or subsoil. This is the zone of accumulation. Finally, at the base of the soil profile is the C horizon, which consists of rock detritus that has been chemically weathered and broken apart, but has not undergone leaching or accumulation. The C horizon grades downward into unweathered bedrock or into unweathered sediment. There are 6 soil-forming factors: climate, substrate composition, slope steepness, wetness, time, and vegetation type. Soil character depends on climate because climate affects rainfall and vegetation. Large amounts of rainfall and warm temperatures accelerates chemical weathering and causes soluble elements to be leached. So we find very thick regoliths and infertile soils in the tropics. In regions with small amounts of rainfall and cooler temperatures, soils take a long time to develop and may retain unweathered minerals and soluble compounds. Vegetation soil-forming factors, different kinds of plants extract or add different nutrients and quantities of organic matter to a soil. Areas having plants with deep root systems help prevent soil from washing away so that it builds into a thicker layer. Deserts have very little vegetation, so they have a very thin layer. Substrate bedrock soil forming factor. Thicker soils develop over a weaker substrate. Different rock types are composed of different minerals, so their soils end up with different chemical compositions. Also, soils tend to develop faster on unconsolidated sediment than on hard solid bedrock. Slope steepness and wetness soil forming factors. A thick soil can accumulate under land that lies flat, and on steep slopes, soils may wash away before it forms. All other factors being equal, soil thickness increases as slope angle decreases. Wetness affects soil weathering rates and organic content. Time soil forming factor. Because soil formation takes time, a younger soil tends to be thinner and less developed than an older soil in the same location. In temperate regions, soil forms at a rate of 1 meter in about 10,000 years. Soil classification, texture, structure, and color. Depending on their evolution and composition, soil comes in a variety of textures, structures, and colors. Soil texture reflects the relative proportions of sand, silt, or clay-sized grains in the soil. In loam soils preferred by farmers, the soil contains about 10 to 30% clay, and the rest is silt and sand. Air, water, and roots can pass easily through the porous space in the soil. In soils with abundant clay particles, greater than 30% clay, the clay packs in the soil is impermeable to water movement. In other words, water can't pass through the soil layers. Soil structure refers to the degree to which soil grains clump together to form beds or clods. Soil structure evolves as soil develops. Structure depends on clay content and organic content, which change over time. Clay content increases with time, and clays form organic mineral complexes, promote soil aggregates, and protect soil organic matter against microbial decomposition. Soil composition controls soil color. Organic rich soils tend to be gray or black. Organic poor and calcite rich is whitish, and iron-rich soil is red or yellow. Soil scientists worldwide have struggled to develop a rational scheme for soil classification. Not all schemes use the same criteria. On this slide is the U.S. Comprehensive Classification System that distinguishes 12 orders of soil based on physical characteristics and the environment of soil formation. On the Oregon coast, inceptisols are the most abundant soil class. Are histosols found on the Oregon coast? If so, where? Examples of soil classification with increasing rainfall. On the left, iridosols form in deserts. Rainfall is so low that no O horizon or E horizon forms, and soluble minerals, such as calcium carbonate, accumulate in the B horizon. In temperate climate, with moderate rainfall, alpha sols dominate, and O horizon forms. They may have an E horizon depending on clay content, and less soluble materials accumulate in the B horizon. Tropical soils on the right are dominated by oxysols, where percolating rainfall or rainwater leaches all soluble minerals, leaving only iron and aluminum-rich residues. They have a very deep regolith and a B horizon. This map is of the distribution of soils around the world based on the U.S. Comprehensive Soil Classification System. Be familiar with the dominant classes of soils in particular parts of the United States. For example, the southeast has ultisols, and the central has mollisols. What about the northwest, the southwest, and the northeast? Human activities such as agriculture, overgrazing, and clear-cutting have led to the destruction of large areas of soils. This destruction results from two processes: nutrient removal and soil erosion. Nutrient removal. Some crops add certain nutrients to the soil, and some crops deplete certain nutrients from the soil. Farming without crop rotation, planting monocrops year after year tend to over-deplete the soil of minerals and inhibit the growth of successive crops. The yield can be increased with fertilizers, but they are expensive and drive up the cost of food production. Soil erosion occurs as a result of deforestation or grassland destruction. Forces such as the impact of raindrops or plowing can break up the soil at the surface and allow the agents of erosion to wash it away or blow it away. When this happens, soil erosion, the removal of soil by wind or running water, takes place. Human activities can increase the rate so that the rate of erosion is far greater than the rate of soil production. Human activities such as agriculture, overgrazing, and clear-cutting have led to the destruction of large areas of soils. This destruction results from two processes: nutrient removal and soil erosion. Nutrient removal. Some crops add certain nutrients to the soil, and some crops deplete certain nutrients from the soil. Farming without crop rotation, planting monocrops year after year tend to over-deplete the soil of minerals and inhibits the growth of successive crops. The yield can be increased with fertilizers, but they are expensive and drive up the cost of food production. Soil erosion occurs as a result of deforestation or grassland destruction. Forces such as the impact of raindrops or plowing can break up the soil at the surface and allow the agents of erosion to wash it away or blow it away. When this happens, soil erosion, the removal of soil by wind or running water, takes place. Human activities can increase the rate so that the rate of erosion is far greater than the rate of soil production.